Hello, my awesome AP Chemers. We're going to talk about formal charges. So formal charges are basically made-up numbers that we assign to different atoms in different structures in order to identify some plausible Lewis structures. So remember that atoms bond together to form these low energy stable compounds. And so to check which structure, sometimes we have a formula and we can draw different structures for it and we're not sure which one is the correct structure. And so formal charges help us figure out which of these structures is the lowest in energy and it's the most plausible. So what you do is you draw the different structures for that formula and you calculate the formal charge for each atom in each of the structures. And to calculate formal charges, what you do is you take the number of valence electrons that are available for that atom, and you subtract the number of electrons that are in lone pairs plus the number of bonds. And we'll do a couple of examples so that you can see what this means. So once you calculate all of these formal charges for each of the atoms in each of the structures, then you see which of the structures is more plausible, because the more plausible structure is going to have all or most or as many of its formal charges equal to 0. Or if they're not all equal to 0, then the most negative formal charge is going to be on the most electronegative atom. So let's do an example of that and try to figure it out. So we have BFH2. And so there are two ways that I can think of to draw this molecule. So I know that boron has 3 valence electrons. So I'm going to use one to bond to the hydrogen, another one to bond to the second hydrogen, and then the third one to bond to the fluorine. And the fluorine has 7 valence electrons, so one is in the bond, and then I have 3 lone pairs. So that's one of my structures. My other structure, I could say, well, this doesn't seem right because the boron here does not have an octet, which is not very stable. And so is there a way that I can make that have an octet? Well, what if I have a coordinate covalent bond? So remember, a coordinate covalent bond is where both electrons come from the same atom. And so what if that fluorine kind of donates its 2 electrons to make a double bond here? So it would look like this. There's my boron with the 2 hydrogens. And then I'd make a double bond with the fluorine, which now has 2 lone pairs. So I've drawn the same number of total available electrons, but I've made my boron have an octet. So which one is the correct structure? Well, you can use formal charges to figure that out. So what we do is we calculate the formal charge for each of the atoms in each of the structures. So that means for both of these structures, we need to calculate the formal charge of the boron, the fluorine, and then each of the hydrogens. In this case, both of the hydrogens are equivalent, so it's okay if you calculate it just once and say both of them are equal. So for the boron, let's start with that for the structure here. So I do the number of valence electrons for that atom. So boron has 3 valence electrons. Then I subtract the number of electrons in lone pairs. So this boron doesn't have any lone pairs, so that's 0, plus the number of bonds. So this boron has 1, 2, 3 bonds. And so that equals 0. Let's do the boron for this structure. So I have 3 valence electrons minus, and then I don't have any lone pairs, so 0, plus the number of bonds, so 1, 2, 3, 4. And so 3 minus 4, that is equal to -1. Okay, let's do the fluorine next. So fluorine has 7 valence electrons available. So 7 minus. And then the electrons in lone pairs. Notice that this is not the number of lone pairs, but the electrons that are in lone pairs. So each electron counts. And so there's 1, 2, 3, 4, 5, 6 electrons that are in lone pairs. And then plus the number of bonds, there's only 1 bond here. So 7 minus 7 is 0. Let's do it for this one. So fluorine still has 7 valence electrons. The number of electrons that are in lone pairs, so that's 1, 2, 3, 4. and then the number of bonds, so there's 2 bonds here. So 7 minus 6 is plus 1. Okay, the hydrogen has 1 valence electron, and again, those 2 hydrogens are equivalent, so you can just pick one of them. If they were not equivalent, then you'd have to actually calculate it for both, but in this case they are. So hydrogen has 1 valence electron minus, and then we don't have any lone pairs, so 0, plus the number of bonds, which is 1, so 1 minus 1 is 0. Let's look at this one. 1 valence electron for hydrogen, no lone pairs, so 0. Oh, it's not writing in between pages. Here. Oh. There we go. So no lone pairs. And then how many bonds? Just 1. So 1 minus 1 is 0. So let's take a look at these numbers. Which one is the correct structure? Well, the correct structure, after you calculate your formal charges, will tell you that the formal charges are all zeros, or more of them are zeros. And if there is a number that's not a 0, the most negative number needs to lie on the most electronegative atom. So this structure is definitely superior for 2 reasons. First, you have all zeros. Here you don't. So that automatically makes that structure better. The second reason is that you can see that the most negative number, the most negative formal charge, is not on the most electronegative atom. The most electronegative atom out of these is fluorine, right? Fluorine has a positive 1, not a negative 1. And so that tells us that this is not a very good structure. And so this is more probable. Just a little note here that when you add up the sum of the formal charges for your entire atom, your entire species, it should equal to the charge of the species. So in this case, this is the neutral compound. So if I add all these up, it should equal to 0. Same thing here. If I add these up, it should equal to 0. So that's one way to kind of check that you did your formal charges correctly. If you add them up and it's not equal to the charge on that species, then something's wrong. A little note for an exclusion statement here. It's saying that, so the new CED came out and said that the use of formal charges to explain why certain molecules do not obey the octet rule is out of the AP exam. However, use of the formal charges to explain why one structure is more plausible than another is still part of the AP exam. And so the way that this was worded, where it stopped here, and the new CED kind of tricked us. And so one year we thought, oh, formal charges are out. But in reality, it's just out for explaining things that don't obey the octet rule. So they would not ask you about this specific example where, it's not obeying the octet rule. But they could ask you to calculate formal charges for molecules that do obey the octet rule. So I honestly think this exclusion statement really is not helpful at all. It doesn't really matter whether it obeys the octet rule or not. You still need to know how to do formal charges. So let's try an example where we do obey the octet rule. And so we want to draw all the stable resonance structures for SCN minus. This is the thiocyanide polyatomic ion. And we want to use those formal charges to determine the most plausible structure that we have. So there's different ways to do this. You can start with your valence electrons and try to account for how many should be there. You could do the math. Let's for fun do the math. We haven't done that in a while to see how many bonds there should be. So, excuse me. So I'm going to do the math on this side here. So remember that you calculate first the number of electrons that you need for all your atoms to be stable. And so we have a sulfur that needs 8, a carbon that also needs 8, and then a nitrogen that also needs 8. So 3 times 8 is 24 electrons needed. Then you calculate how many are available. So sulfur has 6. Carbon has 4, nitrogen has 5, and then remember that negative charge means that you have 1 more available electron, so plus 1 more. And so what's that, 16? Then you subtract the 2, and that will tell you how many electrons are bonded. So that is 8 electrons bonded, which then tells you the number of bonds. If you divide that by 2, this gives you 4 bonds. So we know that we have 4 bonds here. So then you draw your skeleton. So we have sulfur, carbon, nitrogen, connect everything once. And let's see what are our options. So if we need 4 total bonds, maybe we can make them each double bonds. Let's do another one. What's another possibility? Maybe one of them is a triple bond and one is a single bond. What's another possibility? Maybe the other one's the triple bond and a single bond. So then let's put in our lone pairs. So this carbon's good. Each of the sulfur and the nitrogen need 2 lone pairs. Let's check that we've drawn 16 valence electrons. So I'm going to count in pairs 1, 2, 3, 4, 5, 6, 7, 8 pairs. That's good. Put brackets around it because it's a polyatomic ion in the charge. Let's see this one. This needs 1 lone pair. Carbon's good. This one needs 3 lone pairs. Brackets around it. Let's check that we've drawn 16 electrons. So I'll count in pairs again. 1, 2, 3, 4, 5, 6, 7, 8. That's good. Last one. Let's see, the sulfur needs 3 lone pairs. Carbon's good. Nitrogen needs just 1 lone pair. Let's count. 1, 2, 3, 4, 5, 6, 7, 8 pairs. So that's 16 electrons. That's good. So here are my 3 possible structures. I want to know which one is the most probable structure. So if I need to figure out what the most probable structure is, I can assign formal charges. So I'm going to calculate the formal charge for the sulfur, for the carbon, and for the nitrogen. Let's start with sulfur. So sulfur has 6 valence electrons. You subtract the number of electrons that are in lone pairs. So right here I have 4 electrons that are not in lone pairs. Or sorry, that are in lone pairs. 4 electrons plus, and then you count how many bonds are that on that sulfur. So 2. So 6 minus 6 is 0. Let's do it for this sulfur here. So 6 valence electrons minus, and then I have 2 electrons in lone pairs plus 3 bonds. So 6 minus 5 is plus 1. Here, my sulfur has 6 valence electrons minus, then I have 6 electrons that are in lone pairs plus 1 bond. So 6 minus 7 is minus 1. Okay, let's look at the carbon. Carbon has 4 valence electrons minus, then we have no lone pairs plus the bonds. There are 4 bonds here. So 4 minus 4 is 0. Let's look at it here. 4 valence electrons minus, no lone pairs. 4 bonds again. 4 minus 4 is 0. Let's look at the carbon here. 4 valence electrons minus, no lone pairs. And then 4 bonds. So in all of them, the carbon is just 0. Let's look at the nitrogen next. Nitrogen has 5 valence electrons. So 5 minus, then we have 4 electrons that are in lone pairs plus 2 bonds. So 5 minus 6 is negative 1. Let's look at this one here. Nitrogen has 5 valence electrons minus, we have 6 electrons in lone pairs plus 1 bond. So 5 minus 7 is negative 2. And then here, 5 valence electrons minus 2 electrons in lone pairs, and then 3 bonds. 5 minus 5 is 0. just to double check that we did this correctly, if you add up your 4 mole charges, you should equal to the charge on the species. So 0 plus 0 plus -1 is -1. That one's good. Plus 1 plus 0 minus 2 overall is -1. That's good. -1, 0, 0 overall is -1, so that's good. So that kind of helps us reassure us that we've calculated them correctly. So then we try to figure out which of these is the most plausible structure. So which one is it? Are there any that we can cross out? So based on these, let's see if we can cross one of them out. Well, I'd probably cross the middle one out. Go ahead and cross it in yellow here. I would cross this one out. Why is that? Well, both of these have more zeros than that middle one. So that middle one I don't like because there's not very many 4 mole charges that have zeros, and that's not good. The more zeros that you have, the better. So automatically I'm gonna cross that one out. So then between the first one here and the last one, which one's better? Well, both of them have 2 zeros and then a -1. So then remember that we want the most negative 4 mole charge on the most electronegative atom. So which one is the most electronegative atom? Sulfur, carbon, or nitrogen? Well, that would be nitrogen. Nitrogen is the most electronegative out of them. And so we want to pick the one where the most negative number is on the most electronegative atom. And so that would be this structure right here. So this is the correct structure. This is the wrong structure because the -1's on the sulfur, not on the nitrogen.